Have you ever looked up at the vast expanse above and wondered, why is the sky blue? It's a question that has puzzled curious minds for centuries. If the light from our sun appears white, a combination of all colors, then where does that distinct, vibrant blue hue of our sky truly originate? This fundamental question delves into the fascinating physics of light and atmosphere, revealing the hidden mechanisms that paint our world in such familiar shades. The concise explanation lies in how Earth's atmosphere interacts with sunlight. Our air molecules, though tiny, play a crucial role. They preferentially scatter blue light more effectively than they do other colors in the visible spectrum. This phenomenon means that as sunlight penetrates our atmosphere, the blue components of that white light are dispersed in all directions. Consequently, no matter where you look in the sky, a significant amount of this scattered blue light reaches your eyes, giving the sky its characteristic color. This selective scattering is a key principle in understanding atmospheric optics. To understand this, we must first recognize that what we perceive as white light from the sun is actually a composite of many different colors, each corresponding to a specific wavelength. Imagine a rainbow. That's white light broken down into its constituent colors. These colors range from red, which has the longest wavelength, to violet, which has the shortest. The crucial factor here is that shorter wavelengths of light, like blue and violet, interact much more frequently and intensely with the tiny particles and molecules present in our atmosphere compared to longer wavelengths, such as red and orange. This differential interaction is fundamental to how our sky appears. This specific type of scattering, where light is dispersed by particles much smaller than its wavelength, is known as Rayleigh scattering. It's a powerful effect. Even a small decrease in the wavelength of light leads to a disproportionately large increase in how much it is scattered. Mathematically, the intensity of scattered light is inversely proportional to the fourth power of its wavelength. This means that blue light, with its shorter wavelength, is scattered significantly more than red light, which has a longer wavelength. For instance, blue light is scattered about 4 times more effectively than red light, making the blue component of sunlight far more visible across the sky. Given that violet light has an even shorter wavelength than blue, one might logically ask, why isn't the sky purple? This is where human physiology comes into play. Our eyes contain specialized cells called cones, which are responsible for color vision. We have 3 types of cones, sensitive to different parts of the spectrum: short, medium, and long wavelengths. While violet light is indeed scattered more than blue, our S cones, which are most sensitive to blue and violet light, have a significantly reduced sensitivity to the extreme violet end of the spectrum. Furthermore, the sun emits less violet light than blue light. The combined effect of less violet light from the sun, greater scattering of blue light, and our eyes' particular sensitivity curve means that the net result is our perception of a predominantly blue sky, rather than purple. The phenomenon of Rayleigh scattering also beautifully explains the breathtaking colors we witness during sunrises and sunsets. At these times, the sun's rays have to travel a much longer, more slanted path through the Earth's atmosphere to reach our eyes. As the light traverses this extended atmospheric journey, the shorter wavelength blue and green light are scattered away almost entirely, dispersed across the vast expanse of the sky, far from our direct line of sight. What remains of the direct sunlight, the light that manages to penetrate this thicker atmospheric layer without being scattered away, is predominantly the longer wavelength red and orange light. This is why the sun and the surrounding clouds often appear in brilliant hues of red, orange, and yellow during these magical times of day. You can actually observe a simplified version of this atmospheric phenomenon right in your own home. By creating a mini sky in a glass of water, you can visually demonstrate the principles of light scattering. Take a clear glass of water and shine a flashlight through it. Then, add just a few drops of milk, which introduces tiny particles into the water. As the milk disperses, if you view the glass from the side, you'll notice the water taking on a distinct bluish tint, mimicking the scattered blue light in our atmosphere. Conversely, if you look directly at the flashlight through the milky water, the light will appear warmer, perhaps yellowish or reddish, much like the direct sunlight at sunset, as the blue light has been scattered away. This exploration into why the sky is blue is inspired by fundamental concepts taught in introductory physics and various Q&A science discussions. To delve deeper into this fascinating topic and expand your understanding, we encourage you to search for and explore terms such as Rayleigh scattering, which is the core principle behind the blue sky, and visible spectrum, which describes the range of light wavelengths our eyes can perceive. Understanding these concepts will unlock further insights into the wonders of light and our natural world. We hope this explanation has shed some light on one of nature's most common yet profound questions. What other scientific mysteries or everyday phenomena would you like us to unravel and explain in our next video? Please share your why questions in the comments section below. Your curiosity helps guide our content. Don't forget to subscribe to Quickie Explains for more concise, engaging, and informative videos that break down complex topics into easily understandable insights. Join our community of learners and keep exploring the world around you with us.